Welcome back. In this sublesson, we are going to talk about the fundamentals of OSPF version 2. OSPF version 2 is a routing protocol, a dynamic routing protocol in which the neighbors exchange the information and build their routing table. The OSPF protocol was initially defined in RFC 1583 and was later obsoleted by RFC 2178. Now, in this RFC, you will notice that the OSPF routing protocol actually performs the path calculation using the Dijkstra algorithm. The Dijkstra algorithm is an algorithm which calculates the shortest path first towards the destination. You have a bunch of nodes collected together. It forms a hierarchy or a tree structure, and using that tree structure, the OSPF algorithm or the Dijkstra algorithm calculates the shortest path to the destination. Now you must be wondering how the information is available to the OSPF process to calculate the shortest path to the destination. This is all done through the link state advertisements. The link state advertisements, or LSAs as we call it, are flooded to the OSPF routers within the area. When the flooding is done, and remember, this flooding is done when the initial adjacency is brought up. When this flooding is done, the routers or all the routers in the area has the information exchanged by its adjacent neighboring router. With the information exchanged, each individual router will have its own copy of the topology database. Using the topology database, the SPF algorithm is run on that topology database on all the information that it has gathered, and then using that, a shortest path towards each individual destination is calculated. Whichever path is selected as the shortest path is then selected as the best route and installed in the routing table. This information present in the routing table is then used by the router or switches or layer 3 switches to forward the traffic towards the destination using the outgoing interface which has been selected by the SPF algorithm. Now let's dive into OSPF areas. As you look in the topology drawn on the slide, you will notice that this is pretty much an hierarchical model. In this hierarchy, at the top you will have area 0. That means every non-zero area is connected to the backbone area or area 0. By now you must have understood the backbone area is nothing but the area 0. The OSPF area numbers are represented in an IP address format. It can, when configuring or setting up the OSPF links or areas, you can specify a single decimal value for the area, but when you look at the configuration or you look at the OSPF database, it will be represented as in the IP address format. First of all, we have internal routers. The internal routers are the routers that reside within an area. It does not matter if it's part of a backbone area or a non-zero area. The routers that are part of the area itself are known as the internal routers. Then we have the backbone routers. The backbone routers are the routers that reside in area 0. Then we have the ABRs, or the area border routers. The area border routers are those routers which are connecting two different areas. One of the links of the ABR will be part of area 0, and the other link will be connecting to a non-zero area. Thus, an area border router is having two links, or at least two links, which are connecting to two different areas. Then we have the autonomous system border router. The autonomous system border router, or ASBR as we call it, is the router where the redistribution happens from a different routing protocol into OSPF. You might have a service provider link at the edge of the network, and over that service provider link, you might be running a different routing protocol such as eBGP or EIGRP or even static router per se. What you're doing on the ASBR is you are redistributing the routes learned from your external neighbor or external routing or different routing protocol into OSPF. Remember, an ASBR will not be called an ASBR just because it's running two different routing protocols. It will be called an ASBR when those two routing protocols are redistributing into each other, or at least another routing protocol is getting redistributed into OSPF. Since now we have gone through the different OSPF node types or the device types in different areas, now let's go over the different packets that are involved in OSPF. In an OSPF network, 5 different OSPF packet types are exchanged. Let's go through them one by one. The hello packet. The hello packet is used for neighbor discoveries and building adjacencies between the neighbors. The hello packets are sent over a period of time on all the interfaces for the purpose of establishing and maintaining neighbor relationships. The dynamic nature of the neighbor discovery in an OSPF network is maintained by sending these hello packets, which are multicast packets. Thus, the devices should be multicast capable. Then comes the database description packet. The database description packet is used for maintaining database synchronization between the routers. During the adjacency building process, or when the adjacency is being initialized, these packets are exchanged. These packets describe the topological database contents. The database may be described by using multiple packets. Before the DBD packet or the database description packet is exchanged, a master-slave relationship is established. One of the node is chosen as the master and the other one is chosen as the slave, and the information is sent. After the DBD packets are sent by the master, the slave sends its own DBD packets. Then comes the link state packets. The link state packets are divided into 3 parts: the link state request, the link state update, and the link state acknowledgement. The link state request is a request specific to the link state records from another router. The router is requesting an update from its adjacent router. The link state update is actually sent on the request made by the other router. So if there are 2 routers, router A and router B, and A has requested the update, the link state update from B, the request will be sent by A to B, and the link state update will be sent by B to A. The link state acknowledgement packets are used to validate the reliability of flooding of link state advertisements. It is important to note that a single link state acknowledgement packet is used to acknowledge multiple link state advertisements that have happened between 2 adjacent routers. It's also important to remember when you are deploying a network, the routing protocol packets are sent with an IP precedence value of 6. This means that the routing protocol packets are given a higher priority in the network. So be it an OSPF protocol or be it any other routing protocol such as BGP or EIGRP, they are sent with an IP precedence value of 6. Now we'll look into some more details on the OSPF hello packets. The OSPF hello packets are typically multicast packets, as I mentioned before. These hello packets help us dynamically discovering the OSPF neighbors. These hello packets are sent on a multicast address of 224.0.0.5, and it's sent out on all router interfaces. For broadcast packets, the information exchanged or the information sent except the hello packets are sent to the DR and BDR and on the address 224.0.0.6. All packets from DR actually go on 224.0.0.5 address. And we'll see more about these packet information exchange when we are looking at the deployment part or the implementation part of OSPF. OSPF link state packets. The OSPF link state packets are typically in a steady state. That means they are not being exchanged at a very frequent intervals. They are usually incremental in nature. So any kind of network event, say for a link flap or a node reload, will generate an LSA update. But otherwise, the LSA updates are in steady state. They are not being exchanged all the time. A periodic refresh does happen every 30 minutes, but apart from that, those link state packets are pretty steady in nature. These link state packets help us maintain a consistent database. There are separate databases maintained for different areas. So when you're exchanging information from area 1 adjacent routers, a topology database is built using the LSAs exchanged by the area 1 nodes. Similarly goes with the nodes in area 0. Remember that the LSA flooding is restricted to the OSPF area, which means this helps us in having an identical databases on all the routers or switches, layer 3 switches within that area. Let's go over the different types of LSAs that we have in OSPF. In this slide, we are going to cover from LSA type 1 to type 5 and LSA type 7. We are not going to focus on other LSA types as those LSA types are outside the scope of this course. Let's begin with LSA type 1. The LSA type 1, also known as the router LSA, is generated by all routers in an area to describe their directly attached links, that is, intra-area routes. These do not leave the area. It's important to remember that these do not cross the area boundary. The LSA type 2, or the network LSA, is generated by the DR of a broadcast or a non-broadcast segment to describe the neighbors connected to the segment. Again, these LSA type, the LSA type 2s do not leave the OSPF area boundary. The LSA type 3, or the summary LSAs, are generated by the ABR, area boundary router. These LSA type 3s are used to describe a route to neighbors outside the area, that is the inter-area routes. If these summary LSAs are not present, OSPF routers in one area will not know how to reach the destination in OSPF routers or routes in other area. LSA type 4, this is an ASBR summary LSA, which means it's also generated by an ABR, but it is used to describe the route to an ASBR to the neighbors outside the area. Then comes the LSA type 5. It is an external LSA. That means within the area there is an ASBR connected. The LSA type 5 is generated by an ASBR to describe the routes redistributed into the area itself. Now, if there is no redistribution happening, like I mentioned before, a router is not really called an ASBR router. Similarly, if there's no redistribution happening, there won't be any LSA type 5s. The external routes are typically in the form or seen in the form on the routers as E1 or E2 routes. The even routes use a cumulative cost of the cost reported into the OSPF domain at redistribution plus the local cost to the ASBR. That means the cost of the network that is added in order to reach the ASBR. The E2 route, which is a default way of representing an external route, uses a static cost throughout the OSPF domain. Now, this will not really represent the cost to the external network like E1 does. Finally, the LSA type 7, the not so stubby area external LSAs. These type 7 LSAs are generated by an ASBR inside an NSSA area. We'll talk about the NSSA area in a bit, but the type 7 LSAs are only specific to NSSA area. It does not cross the NSSA area boundary. Similar to the external routes, which are the type 5, the LSA type 7 routes are usually seen in two formats, either as N1 or N2. The N2 is a static cost, whereas the N1 is a cumulative cost that includes the cost to reach the ASBR as well. Now, you must be wondering what happens with these type 7 LSAs since they don't cross the area boundary. At ABR, the type 7 LSAs are actually converted into type 5 LSAs and then advertised further. Within the OSPF headers, there is a P bit. When this P bit is set, this P bit allows the ABR router to convert the type 7 LSAs into the type 5 LSAs. And thus, the information from the NSSA area reaches other areas in the network used as a type 5 LSA. Now let's talk about the different OSPF area types. Primarily there are 5 OSPF area types: the normal area, stub area, totally stubby area, not so stubby area, which is also known as NSSA, and totally NSSA area. Normal area. Normal area can be thought of as a backbone area or a non-zero area. A normal area has type 1 and type 2 LSAs, which are primarily used to build their topology databases, and it also has the summary LSAs, which are advertised by the ABRs. Along with these type 1, type 2, and type 3 LSAs, the OSPF area can also have default external route and can have summarized and non-summarized specific external link information. Then comes the stub area. If you have an area which has only one way in or one way out, in such a scenario it would be more sensible to have an area defined as a stubby area. Why? Because there would be no need for that area to learn about external routes which might not be of any relevance to the nodes within that area. In the stub area, we have type 1, type 2, and type 3 LSAs, but remember there are no type 5 LSAs because we are rejecting any external routes within the stub area. Thus, no LSA type 5 is injected into the stub area. In its place, the ABR injects a default route which helps provide external connectivity to the routers in the stub area. Totally stubby area. Now, there might be routers in which you do not even want the summary LSAs to be advertised. In the totally stubby area, the type 3, type 4, type 5 LSAs are filtered and only the default route is advertised by the ABR. When you're configuring or implementing a totally stubby area, only the ABR needs to be configured with the no summary command, stub no summary, whereas all other routers in the stubby area are configured with the area stub configuration. And we'll see more about that when we are implementing totally stubby area or stubby area. The primary benefit of having a totally stubby area is that it has a smaller link state database. That means fewer routes. Here we are cutting down on the type 3 LSAs. That means there are no summary routes and we only have a default route. So you have the route information or the LSA information of type 1 and type 2. And apart from that, you only have a default route coming from the ABR. So any network beyond the ABR is reachable only via the default route. OSPF NSSA area. For NSSA area, let's think of a scenario where you have a stubby area, but you also have an ASBR within that stubby area. You want to inject the external routes from stub area because you're redistributing from a different routing protocol into OSPF. And from the stub area, you want to advertise those prefixes into the OSPF domain. In the NSSA area, after the redistribution happens, the external routes are injected into the NSSA area as type 7 LSAs. These type 7 LSAs on the ABR are converted into type 5 LSA and is then flooded into the backbone area. So in the backbone area, you will be seeing the type 5 LSAs only from the NSSA area. Filtering and summarization of the routes are allowed only at the ABRs. And the default external is configured using the default information originate. So if you're not advertising all the routes or external routes from NSSA area into the backbone area, you can configure default information originate, which will advertise a default route into the backbone area. What this does or helps with is if you want to reach the external network, which is part of the NSSA area across another routing protocol, the backbone area or other areas will use the default route to reach that destination. And finally, we have the totally NSSA area. The difference between NSSA area and the totally NSSA area is that there are now no type 3 LSAs. We only have type 1, type 2, and type 7 LSAs, including the default route, which is injected by the ABR. The type 7 LSAs, as before will be converted into type 5 LSAs and will be advertised back into the backbone area. But apart from these 3 LSA types and the default route, no other LSA is allowed in the totally NSSA area. Now we have looked at the different OSPF packet types, we have looked at different OSPF areas and LSA types. Now let's understand what happens when an OSPF neighborship is established. It goes through several states and different processes or different set of information is exchanged during each stage. And we'll look at the information being exchanged on the light board. So now to understand the finite state machine of OSPF adjacencies, let's look at the 2 routers, router 1, router 2. And let's say their router IDs are 1.1.1.1 and this one is 2.2.2.2. So initially they don't know about each other and they are in down state. So when the first time R1 sends a hello packet to R2, it moves to the init state and it says that, hey, this is my hello packet and I don't have any neighbors, so I'm saying I have null neighbors and my router ID is 1.1.1.1. On the other side, when R2 receives this hello packet and it sends its hello packet towards R1, it says, hey, I'm sending you a hello packet, but now I know about one neighbor which is you. So I'm saying my neighbor is 1.1.1.1. Well, adjacent router ID is 1.1.1.1 and my router ID is 2.2.2.2. So when this information is exchanged at this point, since both of them have exchanged their hello packets, this is in two-way state. And just for clarity, I'm adding this is neighbors and this is my router ID. Once both of them have received the hellos, the first one and the second one, R1 sends a hello back towards R2 and say, hey, I'm sending you a hello, but this time I have a set of neighbors 1.1.1.1 and 2.2.2.2 and my router ID is 1.1.1.1. Once this step is done, the router then goes into the DR election process. It would depend on the type of the network configured on the segment. If there is a point-to-point, if this is a point-to-point, no DR segment, DR election will happen. But if it's a broadcast segment, in that scenario, the DR election will happen in this state between these 2 routers, or other routers in the same segment, which is a layer 2 segment or part of the same VLAN. Once the DR election has happened, or if we have skipped this DR election process based on the network type, the next step is to identify who is the master and slave. And this state, and if I put that back again just for clarity, R1 and R2 will try to decide who is the master and slave among them 2. And during this state, the router is in X start state. This state is where the master and slave election happens. Once the master and slave election has happened or decided which one is going to be the master and who is going to be the slave, say for R1 is the master, it's going to send the database description packets towards R2 and same on the reply. So DDP, the database description packets are exchanged between both of them. And this happens during the exchange state. Once the exchange state is done, next comes the loading state, in which we have the exchange of LSR, the link state request, the link state update, and the link state acknowledgements. This is done in the loading state. And finally, every information has been exchanged, we move to the full state. The full state means the adjacency is established, all the information exchanged between the 2 routers is completed, and we then just follow the regular hello keep alives just to make sure that the adjacency is up and running.